All right, guys, so as we're diving into chapter 4, finally, we are going to continue to look at derivatives, but the whole focus specifically in chapter 4 is applications of derivatives. We spent basically the entire time in chapter 3 just taking can we find a derivative of a certain function, whether that function is a power function, whether it is a product of two different functions, whether it is a natural log, whether it is an exponential function, whatever the case may have been. That's kind of what our prime focus was in all of chapter 3, was just simply finding the derivative of any type of function. And now we're going into chapter 4, which derivatives are not going away. So we have to kind of be able to use what we've done in chapter 3 to go ahead and to put it into some more real life context, some more application, and then dive a little bit deeper into the different parts of a derivative function. And that's going to lead us right into the first part of this video, which is all about the extreme values of functions. So our goals for this video in 4.1 and then a couple ones that will follow about 4.1 as well will be to define and identify absolute and local extreme values. Now, let me kind of preface this video off by saying is that what we're going to look into today, hopefully by definition, has a little bit more of a review for us from pre-calculus. We have looked into finding the absolute and minimum values multiple times in the past from functions. And so let me kind of just make sure that we understand that we're not going to be trying to change the definition of what we know from absolute min and absolute max of the past. But what we're going to do is kind of take it into a different context when we are thinking of derivatives and where it kind of comes into into play. So what the point of 4.1 really is kind of going into basically one of the most useful things that we can actually take from a function's derivative. And that is whether or not the function assumes any kind of maximum or minimum values on a particular interval, of where the values, are found or are located. And so, why is this important? You kind of think about it is, once we know how to find a function's, extreme values, where it has its absolute top point and absolute minimum point, it helps us kind of answer, what is the most effective size of, a certain dose of medicine, or it helps us kind of what is the cheapest route that, we can take, or the least expensive route that we can take for purchasing, I don't know, offshore oil or something of the nature. It doesn't matter what we're talking about, but using the absolute minimum values of that function's derivative will help us answer a lot more of real life application based questions. So that's what we're going to lead us into for today. So I've listed out here some success criteria for us. This is what I believe, and this is all said and done. You should be successful with our goal if you can find absolute and local extreme values. Can you define what extreme values are? Can you use them in regards to the extreme value theorem? And then find and define some critical points as well. And so as we go through some examples over the next few videos, that's going to be kind of what we're going to be looking into as to how to find and to check off some of these success criteria. So let's start off right off the bat by looking at the definition of absolute extreme values. So I'm really hoping as you see this definition scroll through the screen that this is going to be something, a review for us. So if I'm concerned with the absolute extreme value, now I'm going to read the definition and I'm kind of try to paraphrase it a little bit for us. Let's say there's a function f, and that function has a specific domain, and we're going to call that domain D, all right? Let's say there is a y value and f of c. So c is just a random number for f. If f of c is the absolute max, then what we can expect is that every single other f of x value is less than or equal to f of c for every x that is in the domain, okay? And then if it's going to be a minimum, if f of c is going to be a minimum, the only way this is going to happen, that's our if and only if is that if every other f of x is greater than or equal to f of c for all the different x's that are in the domain as well too, okay? So it's not rocket science. It's not trying to be rocket science. It's basically saying your absolute highest point on the graph and then your absolute lowest point on the graph. You can't have an absolute max or an absolute min if there's something either above or below what you are trying to say is your absolute max and your absolute min. Now, one thing I will also say is that when we are talking about extreme values here, you also might hear absolute max and mins be called global max and mins, okay? So just kind of be on the lookout for that as well too. And so I'll put down here global as a possibility that you might see as well. So if you see global, that's what they mean for absolute, either a max or a min. And then you also might hear when they try to get all fancy on us, they might, oh, that's not right, absolute extrema. All right, so you might hear global max and min, you might hear absolute max and min, you might just hear absolute extrema. That kind of just talks about, you know, the max and min as a whole. If it says absolute extrema, just say find both of them is really what it's asking in that particular example. But what I want to kind of start some things off with is just simply exploring what it means to be absolute max and mins on a specific domain. So a lot of times in pre-calculus, we looked at a function, and let's say, for instance, I'm just looking at the function y equals x squared, okay? So that's what I'm going to start out with, y equals x squared, and so we know that roughly, and this is not a perfect sketch, but roughly, parabola looks something of the nature for y equals x squared. So let's say, for instance, I wanted to find the absolute min and max, or the absolute extrema, of this particular function on the interval from negative infinity to infinity. All right, so going from negative infinity to infinity, what are the absolute mins and maxes? Well, we can see here that we are going to have an absolute minimum, an extreme value right there at the vertex of the parabola. So in this case, you're going to see that you have the absolute minimum at x equals 0. So we'll have an absolute minimum at x equals 0. And so then the question is, well, what about an absolute maximum? Well, because this goes off into positive infinity for the y values, we are not going to have an absolute maximum in this case. So we will not have an absolute max. So no absolute max in this case. And that's kind of where we took it in pre-calculus. So now let's say, for instance, I changed it up a little bit and I said now I'm concerned with the interval from 0 to 2, both included. And so now we got to think to ourselves, well, from 0 to 2 is, once again, right here where we kind of had our min before. And then let's say 2 is somewhere over here. I'll say this is a y value of 2 in this particular example. So if that's the case that I'm looking, whoops, I'm not sorry, not on the y value, on the x value. Okay, so now we're looking into account whatever particularly the case is for 0 and 2. So we know we will have, in this case, an absolute minimum at x equals 0. And we're allowed to take x equals 0 into account because 0 is a part of the domain specifically. And then we know that specifically we are going to have an absolute minimum at x equals 2, or an absolute maximum at x equals 2, because that's the highest part. So we're kind of only concerned with this part right in here from 0 to 2. And so if you want to actually find that value of the absolute min, well, the value is going to be 0, because when you substitute x in for y equals x squared, it becomes y equals 0. And the value for the absolute maximum is going to be 4, because we have the max at x equals 2, making the value 4 of y equals x squared. Now let's take one more example into account as to, well, what's going to happen if the interval kind of changes up on us a little bit? What if the interval is not from 0 to 2 included, but from 0 to 2 unincluded? And so I'm going to redraw the graph a little bit down here. And now we have our function, once again, something of the nature that we're seeing here. And let's say we're looking at from 0 to 2 unincluded. So that means we have a hole at 0 and a hole at x equals 2. Well, if this is the case, the only interval we're looking at is still in between here. But at our highest point, there is a hole. So there is no absolute max. At our lowest point, there is a hole. So there is no absolute min in this case. So hopefully that makes sense. And as a whole, we can say there are no absolute extrema when it's all said and done. So hopefully that's kind of making sense to us as to how to use it specifically on a particular interval that we're looking at specifically. So that's going to kind of lead us into what we talk about is called the extreme value theorem. So that's one of our goals of this lesson, was to utilize and define what the extreme value theorem is. So let's talk about the extreme value theorem. Now, it's nothing, again, that we haven't really talked about in the past, all right? But it's something that we kind of need to recap a little bit as well too. So the theorem says if f is continuous on a specific closed interval, most textbooks use the interval as a comma b, so we'll keep that consistent with us. If we have a continuous function f on a closed interval ab, then we can go ahead and say that f has both, I'm going to underline both because it's key, both a max and a minimum on the interval. So we can really use our extreme value theorem in a couple different ways. One, the main reason that we utilize it, guys, is to kind of assure us if we are going to have an actual extreme, absolute extrema. So we can utilize it to say, hey, I know I have a continuous function, there's no gaps, there's no holes, there's no jumps, there's nothing of the nature that's coming our way. And so we can use the extreme value theorem to tell us that this is going to have a maximum minimum, just like we showed in the top, if I can get the thing to go down, just like we did in our top example. If I can get my OneNote to work for me, apologize guys, give me a sec. I should have some good elevator music ready for you guys if this ever happens. All right, looks like we're coming back in. All right, guys, so back to what I was saying is we use the extreme value theorem to kind of give us a for sure account. So like in this concept right here where our intervals from 0 to 2 or 0 and 2 are included, that is a continuous function on that interval. Thus, we are going to have both an absolute maximum and a minimum. But we see here from 0 to 2 where they're not included, we have the holes at 0 and 2, so it's not continuous amongst that entire interval that we're dealing with. So that's why we did not have any absolute extrema in the particular interval and for this function that we were dealing with specifically. And so that's kind of just a good theorem to use as a way just to kind of be a little bit more foolproof when it comes down to it specifically. So as we're continuing to go through the concepts of absolute extrema and things of the nature, what I want to talk about is revisit a concept that we've dealt with in the past called critical point. So we've talked about the critical point in a function, and remember that happens at those spots of the graph of the derivative where we have a cusp or something that where we don't know what's about to happen with the tangent line, so we don't really know what it's going to be specifically. So just kind of for just a reminder's sake of what we said the critical point was, we know our critical point is going to be a point in the interior of the domain. So it's got to be inside the domain. If not, we don't really care about it. So on the interior of the domain of a function f at which the derivative equals 0, or possibly it's not differentiable, or f prime of x does not exist. It's not going to be differentiable. And so we call this a critical point when this happens. So this kind of to sum up our topic of extreme values, we can kind of make the generalized statements and make sure this is copied down, guys, is that the extreme values occur only at critical points and endpoints. All right, let me say that one more time. Extreme values, your absolute extrema, only occur at critical points and at endpoints. That might be kind of common sense for a couple of us, but overall it's a big thing that we need to take away from this as a whole, okay? So we know that extreme values only happen at critical points and at endpoints. Let's wrap up the video with a little example here looking into finding absolute extremes. So let's say, for instance, our first example that we're going to look at for this video is find absolute max and min of the particular function f of x equals x to the 2/3 power on the interval -2 to 3 included. And so let's just kind of think about it, for a sec. When we're doing this, graphically, of course, we can just put this into the calculator and do it graphically and kind of find out where there's a cusp or where there's that max and that min value that we are looking at specifically. But let's say, for instance, we didn't have the luxury of utilizing a calculator. We wanted to kind of confirm it a little more analytically versus graphically here. So in order to do so, the first things first, we have to go ahead and find out what that derivative is going to be, because that's going to be able to tell us where possibly we are going to have a critical point at. So let's go ahead and find the derivative of the function first and foremost. So f prime of x in this case will be 2/3 times x. Well, 2/3 minus 3/3 is a -1/3. So 2/3 times x to the -1/3, which leaves us at 2/3 times the cube root of x. And so that's, when you're solving this one, we don't have a 0, so we're not going to have any point on this graph that this is going to cross the x-intercept, just because we can see that by what the function is going to look like. However, we do have a problem. We are going to have the graph being undefined at 0 specifically. And so because we know that we're going to have a critical point at specifically when this is 0, we know we just substitute what happens at 0 for this function. So the critical point at x equals 0 and f of 0 equals 0 for this case. Once again, we know we have a critical point there because if you substitute 0 into the denominator of the derivative, that's going to be undefined, and that will cause a problem for this particular case. And so now we take that critical point, substitute it into the original function, f of x, and we get 0. So now that's where our critical point is going to be. So now we have to check to see exactly where the endpoints are going to be and what are those values of those endpoints. And so because this does specifically only go from -2 to 3, we know those are going to be our endpoints. So the value at the first endpoint, -2, is -2 to the 2/3 power. Well, this is the same thing as the cube root of 4. And then f of 3, which is the other endpoint, is going to be at 3 to the 2/3 power, or the cube root of 9 in this particular function. And so this kind of is roughly going to be about 2.08 here. And the reason why I kind of only highlight that one is because that's going to give us the maximum value. The cube root of 9 is going to be higher than the cube root of 4, so I know it's going to be higher in this particular example. So what we can make this kind of general statement when this is all said and done and answering the question is that we can see from the list of the functions that we're giving here, we have the absolute maximum, so we have the absolute max at x equals 3, okay, so that's when we know what x equals 3 is. And then we are going to have the absolute minimum at x equals 0 because we had that critical point at x equals 0. And it's going to obviously occur when y value is 0, okay? So the point here will be at 3, 2.08, and here at 0, 0. All right, guys, so that is going to kind of wrap up a little bit for our absolute max and min. That was a little bit longer of a video for us because I had a little bit more to explain in terms of our different types of functions and things of the nature. So what I want you guys to do is give this one a shot specifically on your own. It is f of x equals 1 over x plus the natural log of x over the interval from 0.5 to positive 4. And what I want you to do is just find the extreme value. So find absolute max and min. Come on. Having trouble drawing on here a little bit. Find absolute max and min of the function. I want to go ahead and give you guys the opportunity to kind of check your answers on this as well too. So you're going to see the min at x equals 1 and f of 1 should equal 1 in this case. And then you're going to have the absolute maximum in this case at max at x equals 1/2, and then f of 1/2 should have been 2 minus the natural log of 2, I believe. 2 minus the natural log of 2 in this. So you kind of give yourself a shot. Remember, first step is find that derivative, find out where your critical points are going to be in this particular example, and make sure that is on the derivative, on the points from 0.5 to 4. All right, guys? So that'll do it for this particular example.